Okay, so we kind of learned most of the things that we need for logic, or that we'll cover for logic last day. But let's see here. Add a page. I want lines. There. I'll bump these around, but it's kind of annoying. Just for some review, we started logic, in case you missed it. And so, which is not in the textbook, right? And so it's what you're expected to know is just in this handout, and there's lots of exercises for us to do today. And so we'll kind of do a mix of you guys working on them, maybe together might be nice, or not, whatever. You can do them on your own if you want, but it's more fun in a group. Right? And then we'll go through them together. Okay, and so we introduced kind of and, the logical and, which we use, just as some review, we use an upside down V, right, to denote and. And so if we have a proposition, I should have done that first. A proposition P, a lowercase p is usually a proposition. And what do we mean by a proposition? Anything, any statement with that we can attach a true false value to, right? And so things like it is Tuesday, that's true, right? If I told you, hey, today it's Friday, that's false, but it's still a proposition, right? And so you can attach a true or a false statement to it. And so a true or false statement. And so we can have multiple propositions, and we talked about the logical and, right? Where, what did the truth table of PQ, we started introducing these truth tables as a way of summarizing all the possible ways that P and Q could be could work together. Oh, you know what? Before we introduce the truth table, how about we just talk about all the connectives that we introduced, right? And then we'll make a big truth table with all of them. Okay. And so we introduced or, which is the capital V, or I guess, yeah, it's not really a V, but it looks like a V. And so we have and, we have or. Do you remember the if then was this arrow, right? So if P then Q. Right. We worked on the conditional, right? So this is called the conditional. A conditional statement. From the conditional, we built out things like the contrapositive, the converse, and the logical inverse. We'll leave that in last day, right? You'll work on it some more, but for review, we don't really need it for what we're going to do today. So it was fun while it lasted, though. And so we have the if P then Q, and we have a not, which I use a little hook, right? So not P, for example, right, is the negation. So you just flip the truth value of these things. What else did we introduce in terms of connectives? Let me see here. Luckily, I have my little go-tos here. Oh yeah, we did the biconditional, if and only if, which we usually abbreviate IFF, which I'm not sure I introduced last day. Let's see here. IFF is shorthand for if and only if, which uses the double-sided, the biconditional, right? So it has to go both ways. What did we find with the if and only if statement, right? It's only true, only true if the values are the same, right? Going between 0 to a 0 and 0 to a 0 back again, or a 1 and a 1, right? Bouncing between the same values. Only true if in P, if and only if Q, only if P and Q have the same value, have the same, usually we call it truth value, right? It could be 0 for false or 1 for true. And then I think that's all we introduced last day. Nice. We put these into a table, right? All of these can be built off of just a P and a Q. And do you remember how to make that generic start? We're gonna have 0, 0, 1, 1. And that's because I want to look at all the possible combinations of P and Q. And so if we start at 0 for both of these, then Q is going to alternate 0, 1, 0, 1. Now we've looked at all the possible combinations of truth values. So if we start with the and, right? And if we made a column of P and Q, then P and Q would be, if it was 0 and 0, so false and false, well, that's going to be false. Right? If you have a false statement and a true statement, well, the overall statement is false. You have a true statement and a false statement, the overall statement is still false. The only time that the and is true is if they're both true. Right? The or is a little bit more flexible than that, right? If we're thinking about statements like, I'm sitting on a chair, or I'm standing up, that's true, right? And so just one of the things has to be true for the overall or statement to be true. And so don't get kind of bogged down. You want to go back to this P or Q over here. And so 0 or 0, well, that's 0, but 0 or 1 is a 1, and 1 or 0 is a 1, and 1 or 1 is a 1. Those would be true. What the conditional? If P, then Q. This was the one where we did that example of if you get 95 or higher on the final exam, then you'll get an A in the course, right? And we looked at all the different combinations and all the different outcomes. And the only one that was false, right, was if we started with a true value and went to a false value, right? And so, but starting at a false statement and ending up at a false statement, that gives a true overall statement, right? And that's kind of confusing to me, I think, right? And so let's see here. Where was it? Yeah. Yeah, if you receive a grade of 95 or better, yeah, I remembered it pretty good, then you'll receive an A in this course, right? You didn't get 95, You didn't get an A. That's okay, that's still overall true, right? You didn't get 95, but you got an A. That can happen, and that's still a true kind of valid statement. Right? You got 95, but you didn't get an A. Hey, then they lied. They lied to you. So that's a false statement. And then you got 95 and you got an A. Hey, that's great. Then that checks out. If you look at, we can look at not P, for example. Right? The negation, we could find the negation of any of these values, right? And so, but let's start with not P. You just switch the sign or the logical truth value, right? So a 0 becomes a 1 and a 1 and a 0 and a 0. There must be something in this room just dries out my throat. Exactly. Incepted. Or maybe it's all of us. Dry. Okay. Last one. If and only if. Which is, we made an extension of this one, right? But now we're going to do the same thing going, so if Q, then P, so moving the other direction, right? And then they have to both match. How about this for our review, because we'll look at it some more. For the biconditional, P if and only if Q, said, okay, well, that's going to be true if they just both have the same values, right? Otherwise, they're bouncing between two different values. And so between 0 to 0, right, that's going to be true, but 0 to 1 and then 1 to 0, right? One of those ways is a lie, making this false. Next one false, and then 1 to 1, bouncing between these is true. It could just be a matter of memorizing these truth values, right? But with a little bit of practice, a lot of these start to kind of come naturally, right? And so you don't really need to memorize them maybe, right? The only tricky one, I think, is the conditional, right? And also the biconditional. But the conditional is kind of more common. Okay. So today, we're going to build a truth table like this, but for a bigger statement. Okay. So let's see here. Okay, pick up here on Tuesday. Well, we didn't really pick up there, but delete. So we've got a compound proposition. Well, any questions before I do? Just bulldoze through. Yeah. Thought that was going to be a question. No, just a cap on. Yeah. So we've got this compound proposition. It involves P. It involves Q. It involves not Q, but that's still coming from Q. And I've also snuck in a little R, a third proposition. That's okay. But what happens is we need to make a longer truth table, right, to account for all the different possibilities. Okay. And so here we have 3 propositions. Which is going to require 2 to the power of 3 rows in our truth table, which is 8. We haven't done the combinatoric section yet, but it's because each of these propositions have two possible outcomes, right? True, false. And so that's why we have 2 and then as our base, and then there are 3 of them, so 2 to the power of 3. Okay? And so 3 propositions, which will require 2 to the power of 3 rows in our truth table. And that is written here in way wordier ways, but nice to have it. Okay, so to set up a truth table for 3 values, and that's as far as I'm gonna go, right? Because 2 is a little bit boring, right? Then you only have 4 rows and there's only so much you can do. But with 3, there's a lot that we can do, right? And so I'm gonna make some columns, P, Q, and R. And knowing that we need to have 8, we follow the same procedure as we did for the 4, right? We did half of them zeros and then the other half ones. So now knowing that we have 8, we're going to have 4 zeros followed by 4 ones. And then we cut that in half and we alternate, okay, like this. 0, 0, 0, 0. 1, 1, 1, 1. Let me bump this up so it's not so crowded there. So then my Q, I cut the zeros in half, right? And I want to alternate 0, 0, 1, 1. And then I do the same thing for the ones. And this procedure, it just is to make sure that we cover all the possible outcomes, right? And it's just nice to have this this kind of way of always doing it and always setting it up. So then for the last one, by the same method, right, with the zeros, we alternate between 0, 1, within the ones, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Let's see if I can add some lines here without making a complete mess. Probably should have drawn the lines before, huh? Oh well. So if we want to build out this C, this compound proposition, right? What you want to do is build the little pieces and then slowly put them together, right? And so what we want to build is we want to build a truth table for P and Q, or not Q and R. And so what I would say is, let's build just a column for P and Q, right, separately. I like to make a new column for not Q because otherwise I get so confused and I just can't flip them in my head. So I just like to have a new column of not Qs, and then I can build not Q and R relatively easily, right? If you can do it in your head, that's cool, but I cannot. So I'll build one there, and then I'll build a new column for not Q and R. And then finally, once I have a column for P and Q, let's call this, I don't know, A or something, just so I don't have to write it out so much. Okay. And let's call this B, right? Then I want to find the final column, which is A or B, right? Just looking at those columns that you've made, kind of ignoring P's and individual P's and Q's now. Okay. And so you want to take it nice and slow, and because you have it on your printout, right, down below here, there are rules for the order of operations, right? What order should you do these things in? Because we have brackets or parentheses in ours, it makes it relatively easy to see which order to do them in. And we'll do some practice with the brackets and stuff, but for now, so there are rules coming our way, but let's start with, where do you want to start? Let's start with A. So let's start with P and Q. So we're going to make a new column of P and Q. Make sure that you're kind of keeping your fingers on the ones that you want, because we also have R now, so you don't want to be jumping around. And so P and Q, remember, they both have to be true in order for the overall statement to be true, right? As long as there's a false statement in there, then the and is false, right? And so 0 and 0 is a 0, 0 and 0 is a 0, 0 and 1 is a 0, 0 and 1 is a 0. Hey, 1 and 0, 0, 0, 1, 1. I don't know. It is exciting to get some ones, though, some true statements. Okay. So to build out B, or what I'm calling B, I'm first going to make a not Q column, right? The negation of Q. And so I'll just sneak that in here. Not Q, and everything in Q, you flip the switch, right? And what's funny is these things are operators that are used in building hardware, right? So microchips and things like that. And so these zeros and ones are actually switches of on and off, right? And it just kind of passes through, and so that's kind of cool, I think, binary operators. But so they are really switches, on-off switches. 1, 1, 0, 0. Okay. So now that I have not Q, now I need to find not Q and R, right? And here the order doesn't matter, right? And so R and not Q is going to be the same, so you don't have to rewrite the order or even read them differently, right? Just make sure that you're going between R and not Q. So I definitely use my fingers for this if you've drawn them out, right? And so now let's make a new column of not Q and R. Okay, 0 and 1 is a 0. 1 and 1, hey. 0 and 0 is a 0. 1 and 0 is a 0. 0 and 1 is a 0. 1 and 1 is a 1. And 0, 0. My table's all slanty. So now we're ready to build C, the overall statement. Right? And so here, if we call this, we call it A, and if we call this B, oops, then we want to find A or, I guess I should use B, or B. in this overall statement C is A or B. You don't have to use those shorthand column names because these are relatively short. Eventually you will have column names that you really don't want to write out again, right? And so I just want to show you that you're allowed to give them kind of shorthand descriptors and use that in your next column. Okay, so now, well, now we're just doing the same thing. We're just doing an or, but between this column that we created and the B column that we created. Right? And for or, right, this is or. So or you just need one of these to be true, and then the overall statement is true. So now, and I have to kind of use my fingers. 0 or 0 is 0. 0 or 1 is 1. 0 or 0 is 0. 0, 0, 1, 1, 1. And now you know the combinations of P, Q, and R that generates true statements for that overall compound statement C. And so here, right, this second row where P is false, Q is false, and R is true, that generates a true statement for C. And then we have to wait all the way to the bottom here, where P was true, Q was false, and R was true, and etc. I don't want to read all these. This is as far as we're going to take this. And so, but if you think about kind of legal arguments, right? Legal arguments, you can break them down into true, false statements. So they are propositions. And so then, right, you can figure out which combinations would give you a true overall statement for whatever compound you're trying to build. Or a computer system, lots of different things. But I like the truth tables, and that's as far as we're going. So that's nice. Any questions so far? Okay. Here, I forgot to remove some kind of scary looking stuff. In general, if C is generated by n simple propositions, so we had 3, right, P, Q, and R, then the truth table for C will have 2 to the power of n rows. So that's fine. We already said that, right? We had 3 propositions, simple propositions, and we needed 2 to the power of 3, which is 8 rows. And this is the part that I probably should have cut if I had read it more carefully, with the first n columns being an enumeration of the n-digit binary integers. It's true, but we don't need to know that. It's true though, but still. In case you're reading it later, you're like, what happened here? All of a sudden we're talking about n-digit binary integers. I know. Do you guys know what binary integers are? So a binary digit is only comprised of zeros and ones. And so to denote, so it's working in base 2. We work in base 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go back to 1, but add a 0, right? 1, 1, 1, 2, 1, 3, 1, 4. And so binary does that too, but only works in base 2. So you cycle through 0, 1, 0, 1, 0, 1, 0, 1. And so this 0, 0, 0 is how you denote 0. 0, 0, 1 is how you denote 1. 0, 1, 0 denotes a 2. 0, 1, 1 denotes a 3, 4, 5, 6, 7. That's it. Because I only have 8 rows. You need another one and get 16 digits, and then you could keep going. Any hoodle. That's more if you're in computer science. You need to know that, working in different bases. Just kind of mind-boggling. But fun. Maybe it's fun to know that it exists. Did you guys know Babylonian math worked in base 60?
Yes.
Crazy, right? I can't even, yeah.
That's where we get minutes and hours from.
It is. I know, right? Wow. Pretty cool. But I think that's the only remnant though in base 60 that I know of. And then we move to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All these kind of old bases. But now we work in base 10, right? But you can work in other bases. Okay, where's this hierarchy I've been talking about? So we've got this hierarchy. On the test, I'm not going to expect you to remember the hierarchy. I'll give you brackets, right? And so as long as you kind of start inside the brackets and work your way out, right? I'm not going to try to set you up. But because here we have the list, then we'll do some practice with it, but it's not something that I expect you to remember, okay? It'll start kind of coming to you naturally, but like I said, it's not worth memorizing. So if there are no parentheses, so brackets or parentheses override this order. So that's how you would override it. But first you would do negation, right? So clean slate, if you see any negation, you start there, and you would start by building out your truth table with any negations that you need to do, right? Conjunction. Conjunction is and, which is upside down B. Making disjunction, a disjunction is or. So first you would do your and then you would do your ors. If you think about BEDMAS, right? Brackets, exponents, division, multiplication, and addition and subtraction, right? That's the order that you do it in. It's pretty similar. What's kind of fun is division and multiplication and addition, subtraction are actually on the same level. And so for those, you would do them in the order that they appear, right? And so for multiplication and division, right, you just do them in the order that they appear from left to right. What's kind of fun is and is kind of like a multiplication, right? And so that's why it comes first. And then the or is kind of like addition, right? And so, right, if you go back to your truth table, if we think about P and Q, right, if I take 0 times 0, I get 0. 0 times 0, I get 0. All the way down until I have 1 times 1, I get 1. Right, 1 times 1, I get 1. And so that works. If we did the ors, right, 0 or 0, right, 0 plus 0 is 0, okay. 0 plus 0, 0 plus 1 makes 1, right? And then 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. It stops working at 1 plus 1, but that's because it can't be really on, right? It just stays at 1, right? And so 1 plus 1 is 2, we know that, but we just keep it as 1, right? So that's the only flaw in using addition and multiplication, right? Instead of just remembering what they do. And so here, this is kind of like multiplication. And this is kind of like addition. Oh yeah, the negation is this little guy, a little hook. The conditional operation is the fourth thing that we do, right? If P, then Q. And then followed by the biconditional operation, which is the if and only if. Within any level of the hierarchy, you're going to work from left to right. So if we use these rules, for example, if we have P and Q or R, then, well, I guess it's here. And comes before or, which is why we would put brackets around the P and Q and then do or R. And these rules are, of course, universal and are used by computers. There. So just as an example, I want to give you some time to just work through, use these and use parentheses to see if you can clarify the order of these operations. First one's kind of tricky, I think. And throw as many brackets on there as you want. Right. Just go nuts. I guess how many brackets can you use? You don't have a handout. Let me pause this. I'll go print you a copy.
What is the proper terms? Let's take the class.
Wow, nice. So this one, I say is sneaky because these are on the same level, right? But within any level of the hierarchy, work from left to right. Bink, bink. And then you don't need any more brackets, but you could if you're showing off.
No, I thought it has to be there.
I'll remove them. They don't have to.
No, we're not gonna ask.
Oh, ah.
Yeah, yours is gonna be-
What about the next one? You'd have to do your negations first, right? Negation comes first in the list. And so you want to make sure that you wrap these up in brackets. And then do the or. So far, so good. Well, here, you have to do the negation on the P and then negate that, bringing you back to P.
But that's what
Yeah.
relevant right now.
It just brings you back to P. We're gonna see that it's equivalent to P. Right? It's got an equivalent logical meaning as P. Okay, here's a doozy. Everyone's waiting for me to do it. What do you think?
Yes.
Tricky, tricky, tricky. And then that has to go to there.
Guarantee you, that's the only thing I'll ever do.
I love how you're doing your friends.
And then if you're showing off.
I'll get fancy, yeah.
But you don't have to.
Sometimes it's so fun.
Right.
Just like you are doing.
Now check this out. I didn't give you space to do all these truth tables, but there's a lot of practice. What I want to do though is finish kind of the examples that we're going to work through, and then you'll have time to work through these kind of depending on, you know, time and stuff. So how's that? Because here, well, this one you can do. Just build a truth table. You've just got two propositions. Here you've got 3, right? So then you need 8 rows, kind of a bigger job. Here's a big compound statement, but really it only involves 3 propositions, right? So you'll need 8 rows again. And oh, you don't need to do 4 propositions. Sorry about that. You can scratch F. That was an oversight. How many rows would you need for 4 propositions? 2 to the power of 4. Ooh, the math's not coming. Too many. Two, 4. Yeah, is it 16? Yeah, probably 8, 16. Too many. Nah. Let me check the other ones. Oh, they're just itty bitties. So what we were talking about earlier, where not P is the same as P, brings us, is that a balancing hand or a question hand? No,
Me?
yeah.
No,
Good.
balancing.
Hypersensitive. Pen caps on. Question. Ask me anything. So we're going to do equivalence and implication by example. And so we're going to compare the truth tables for these 2 statements. The negation of P and Q, and not P or not Q. Spoiler alert, they're going to be the same, meaning that they're logically equivalent to each other.
You ruined it for me.
I said spoiler alert. We're only dealing with P and Q, so we only need 4 rows, so that's nice. Zero, 0, 1, 1. Zero, 1, 0, 1. You can build this out any way you want. And so I'll build it out here, but we'll talk about it later. So if you want to try it, you can try it, see how it goes. And then we'll check in. if I can do this right. I really need to incorporate lines in my printouts. Start all lofty. Like, scrunches up. So the columns that we're interested in are these two. It just depends on how your brain works, how you want to tackle these truth tables. But I like to just start on the inside, P and Q. So I make a P and Q and then I negate it, right, in a new column, because otherwise it becomes really difficult for me in my head. And then to build out the not P or not Q, I did a column of not P's, a column of not Q's, and then I did not P or not Q, right? And I'm able to look across. But what you'll find is that notice that these two have the exact same truth values. And so these statements have the same truth values. Which means that they're logically equivalent. Therefore, they're logically equivalent. You could take it one step further and say when the biconditional operator is applied to them, then the result is going to be true in all cases, right? Because the biconditional, which is this little guy, the if and only if, right, has to bounce between two of the same values. And if these columns look the same, right, then bouncing between 1 and 1 and 1 and 1 and 1 and 1 and then 0 and 0, right, that would give me a column of all truths for that biconditional statement. And so when we get a result that's true for all combinations, right, of P and Q, then we call it a tautology. It's kind of fun. And so a tautology is any expression where it's always true for all cases. And usually this should be a bold number one, but I just want you to call it a tautology, right? And usually I kind of lead you down the path of confirm that this is a tautology, right? And so then you know that the final statement should have all ones, right? And so, for example, use a truth table to confirm that each of the following are tautologies, right? That's kind of nice. You know what you're building towards, and if you don't get all ones, then something went wrong. I know, we're ripping through this thing. So all ones in the final column. So once you've built all these, you want to have all ones, and that makes a tautology. And so what we'll do is we'll hold off on working through these, and I want to talk about what a contradiction is, but I think you can kind of figure it out. It's all zeros, right? And so so you'll get to go back and work through these, but I want to give you more time than just a little bit of time. So a contradiction is anything that's false for all cases, right? All zeros in the final column. So sometimes I would ask you confirm that this is a contradiction, right? Which implies that you understand what a contradiction is, right? You show that you end up with all zeros, right? And there's another example to work through, one simpler than the other. We've already mentioned equivalence, right? And so if we have some tautology, and so for some reason it jumped to R and S. That's for some reason is me, but I'm the problem. It's me. But if R and S or P and Q, if you prefer, are equivalent if and only if R, if and only if S is a tautology, right? So bouncing between them, it basically means they have all the same truth values, right? And so really for equivalence, maybe say, where can I put this? All the same truth values. Right, so you can build it back to the biconditional, and then if the biconditional is a tautology, then sure, they're logically equivalent. Right? Or just if they all have the same truth value, then the biconditional is always true, and then they're logically equivalent. And so there are some common equivalences, right? Things we've used already, like P or Q can be rewritten as Q or P, right? Order doesn't matter. What's kind of interesting is, and we've seen this one before too, if I have if P then Q is going to be logically equivalent to not Q, if not Q then not P. That's the logical inverse. Right? I think it was the logical, was it the converse? One of the ones that are logically equivalent. I don't know. Just need to make it stable. And finally, I think it's finally, the implication, which is kind of a mini version of the equivalence, right? And so if we have if R then S, if we get a tautology, so all ones, then we would say that we just rewrite it with a thicker arrow. And so then we write R implies S, right? So this is an implication. It's kind of a special case where this conditional statement yields a tautology. Right? And then I've got more examples or more exercises for you to work through. And so I guess I need to cook up an assignment for some work for you to submit, or maybe not. Do you want to submit work for this one or no? No. How about this? I'll pull, just like the homework questions, right? I'll pull the test questions from this handout. I'm not gonna go beyond this, right? So, I'll start plugging away at some solutions, right? And you can do the same. And that's all I needed to say about logic, I think. But then don't forget about all these exercises. I know. Oh, remember this? When we used the sentences? Oh, it was just last week. There is De Morgan's laws, which De Morgan's happens or it comes up in lots of different fields. And so you might have heard of De Morgan's. Have you heard of De Morgan's laws? No? Well, here it is. So if you have P or Q and you negate it, right? Then what we saw in our truth table that we just made is that that's equivalent to not P and not Q. So essentially when you distribute this negation inside, which you're able to do, but then what happens is it flips the sign, right? And so you can sort of distribute this negation inside as long as you flip the sign, and that's De Morgan's laws. Works for ands as well. If you have P and Q and you negate it, that's logically equivalent to tossing this negative onto the P as well as the Q, but then you have to flip the sign. Right? That's kind of fun. And we'll see that more with sets. It's the same. Womp womp. Okay. Now I let you fly free through these exercises. Where did we stop doing the stuff? Oh, here. At the top of page 6.
We'll try our best.
I'll stop this recording though. Yeah, because then I'll post the solutions. I think that makes more sense.